If we want to call it a vacuum, then we have to have no charge, which means that there's not going to be any of this thing right here, the charge density. So we got 0 here instead. And there's not going to be any of this thing, which is a current. So there's going to be 0 of this here. There's a couple of tools we really need to solve this. First, we need the wave equation. And so that's going to be something like d over dt squared. This is the second derivative of y is equal to velocity in the x direction. And then we have a second derivative of x. This is spatial of y again. This is just a little vector identity. Here's where the fun starts. So we look at this cross here, and let's just apply it to this b right here. So we're going to say that, we'll go over here. We can say cross it with this b. If we do it on this side, we have to do it on this side. So we kind of have to cross this over here. Let's deal with that a little later. First, let's complete this this part. So we're gonna have the novel again. This time we just plug in the b instead of a. All right, it's nothing too crazy. We have to cross it with this, and then we kind of put this whatever we had right in there. Oh, this is for, yeah, correct. Awesome. Let's do the same thing for e before we do anything. So cross it with e, and we're just gonna get the same thing again over here. This is more just about executing the move a few times so you realize what you have to do. It's not too complicated. And here we're just gonna again apply this nabla to the other side of this equation. So we're working with the e version this time. So then we just go negative d over dt of b. It's kind of what we have here, there. Same thing on both the b and the e. That one using this identity. Now we can try to simplify this a little bit, because if we look at this, we see that both of these are actually equal to 0. So let's just get rid of all of this. This is all just equal to 0, and even that stuff. So then we're just left with the second spatial derivative here, negative, and then we have to sort of simplify this. Let's try to simplify it a little bit by pulling out the time derivatives. Pull the time derivatives out, and then also these constants. And then we kind of have left this cross e. Over here, same type of thing. We have a negative, and then this cross b. Well, that's right, what we have so far, just to simplify things a little bit. So negative spatial derivative here of b equals this time derivative u naught e naught, and then this. Turns out that that is actually equal to this. So let's just kind of consider that. It's supposed to be actually equal negative d over dt of b. And because of that, notice how these pluses are going to sort of, negatives become pluses there. A little bit sloppy, but what we can do is rewrite this as the second time derivative. Then we have this mu naught epsilon naught, and then there's a b. Okay, so we kind of get the second spatial derivative. I'll write that over here. What is this? But this is really second derivative spatially of that. So now we have this, and we can kind of do the same thing with our negative second derivative of e. And that's equal to this stuff over here. Well, let's cross out those pluses anyway. So plus and plus. We got the plus sign already. That's supposed to be equal to d over dt of this. And that's just equal to that one. Just put that in there. Mu naught epsilon naught d over dt of e. So I was just taking this, which is equal to here. It's kind of a little bit complicated, I suppose, but I think we are kind of set up to be able to say that this is the second time derivative. And there's an e here, and that's going to be, again, the spatial derivative, second order. All right, so we came to the same conclusion for both of these variables, e and b, and this tells us that they're waves. Well, since they're waves, we know that the general solution of a wave is kind of the amplitude times cosine kx minus wt, and we realize that if we have a velocity in the x direction, it's also equal to w divided by k. At this point, we should kind of guess our answers. It's going to be something like e cosine of kx minus wt, and then there's b cosine of kx minus wt, and these are supposed to be our e's and our b's. Let's go ahead and mark that this would be probably in the y direction, this would be in a z direction, that would give us the velocity over here in the x direction. Let's go ahead and try to confirm our answer. Let's plug this into the second time derivative over here. So we got like a d squared dt squared. We're just going to do it for e. And that's going to give us, we have to take this derivative twice from in here. It's going to be a little bit complicated to do this. So cosine twice derivative is negative cosine. We also have the e, which stays. We have these two, which also stay. Then we have to kind of take this derivative twice. We get a positive w squared. And then we could throw in our cosine kx minus wt. It's kind of a little bit crazy on that left side. On the right side, it's just going to be similar. So we have a negative, let's take the k squared. Then we have our e and our cosine. All right. At this point, we could finally start crossing things out. We get this cosine will go away, these epsilon, or this e's will go away, and then we're kind of left with the idea, well, these negative signs will also become pluses. And then we have what's left, k squared over w squared. This is omega squared, really. And we have mu naught and epsilon naught. And this is essentially what we wanted to see. So this is great.